Hi everyone, and welcome to this video. So today we're going to implement logistic regression in R, and it's a follow-up to our video introductory to logistic regression. If you haven't checked it out, ensure you see it above here. And the example we're going to use today, we're going to implement using data from a medical field. And the data that we have here, I've sourced it from Kaggle. And we can just go ahead and see the variables that we're going to be working with. So our task at hand, it will be to predict. We'll be trying to predict the presence of diabetes, yes or no. And 100,000 patients were enrolled for a study between different periods from 2015 to 2022, I think, in the United States. And some of the variables, both demographic, both medical data, they were collected, and our task will be just to see how do they associate with the Y variable. So I've gone ahead and imported the data into my R software, and also I've added a link to in the RMD file that I've added in my GitHub. I've added the link to this Kaggle repository where we found this data. Just a summary of our process. So we're going to begin by loading the data and then perform some minimal data cleaning because the data was already cleaned to some extent. Then we're going to do EDA, although our focus won't be much there, but it will be just exploring, getting to know how our data is before we split the data into train and test sets. Then we build the logistic model using the GLM function in R, and we'll then evaluate our model, making predictions using the data that we split into the test. And finally, we'll just generate an output of the model using the GT summary and also maybe another package, the SJ label and the SJ plot. So onto it, go ahead, and I've imported some of the packages, readr, to enable me to read my dataset, which is in CSV format. I've also imported dplyr for data manipulation. I've imported GT summary, and this allows me to do publication-friendly tables. And I've done also for visualizations, I have ggplot, ggthemes, and plotly. We also have stringr for string manipulation. Okay, so here we go. Our data, we can just go ahead and just exploit and see how it looks like from what we have. You can see that the variables, just as I showed you in Excel, are here. We are not going to work with the clinical nodes, so some of the variables will be dropping it in the data cleaning process. You can go ahead also and check the structure of your data. We have numeric and character variables such as the locations. We also have clinical nodes that I mentioned that we may be dropping it. From the HMISC package, this HMISC package here, you can be able to use the describe function, which gives you a detailed description of the data. It gives an in-depth exploration. For numeric variables, it gives the summary statistics, mean, median, gives you the frequency, it gives you the proportion by the frequency. Then for categorical, it gives you the frequency also, and so forth. So the first manipulation that we're going to do for our data, if you go ahead and explore the column smoking history, so diabetes dataset and smoking history, we see that there are 6 classes. There are 6 classes in the variable. So we have current, evers, former, never, no info, and not current. So for the purpose of this analysis, I decided to go ahead and just reduce them so that we have 3 classes. And this will be having current, somebody is a current smoker. And then we'll combine ever or former or not current. We'll combine them to form former stroke ever, that they've ever smoked. And then for no info and never, we're going to combine them and just assume that they are not current, although no info are major, but smoking prevalence is not major in the population. So next we're going to just do that using the case when syntax, and what it does just takes, we use a tilde sign. So we use case when smoking history equals to current, return current, and so forth. Then lastly, I added this to titles because we have this never, and we just want to return everything in title case. So when we go ahead and just rerun the code that we had here, the one for the table, and just see it, we see that now we have the 3 classes that we are interested in. I see our data didn't have any missing values. It was a little bit clean. Then we are going to drop the clinical notes, because we've mentioned this is not what we are using. Next, in our data set, we had the BMI column, and BMI is a calculation of weight in kilograms divided by height in the square of the height, which is in meters squared. So this is what we have in BMI. I just wanted to go ahead and classify, because the BMI category usually gives more value compared to the BMI numeric value. So I added this table here, which is the classification from CDC and children, and for children and adults. So this is what you're going to do, and this is what you implement here, so that if somebody is below 18 and their BMI is in the 5th percentile, you confirm them to be underweight. So this does that, and we'll see the summary in the below. Just a quick overview of our response variable. We see that 8.5% are diabetic and 91.5% are non-diabetic. So our data is highly skewed. Our classes are very imbalanced, but that's not the focus of our today. We'll just focus on just writing the model and just understanding how the model is interpreted. And then in later videos we'll see how we handle this, so that we have a very good model. You can go ahead and just even see a summary using the GT summary package, and you'll tell me if you want a detailed description of how to use this GT summary. I really love it because it gives publication friendly tables. So we can see it's just like having the pivot table in Excel. I can go ahead and just see here we have our year variable. We see that majority were enrolled in 2019. We also have the age. See the age, the minimum individual was 80 years. The maximum was the minimum was 0. The maximum was 80. Then the mean age was 42 with a standard deviation of 23. The median was 43, Q1 and Q3 as shown there. Then we can also see other variables, such as now the BMI class that we created. You can see that we have 35% being normal weight. We also have some overweight here, 42%. Then we have 12% obesity, severe obesity 11%. The GT summary table, you can also just go ahead and also do it by the Y variable, just to show the differences, how the distribution is. You can also add a P value. When you add P value, you'll be able to see how each variable compares to the Y variable. And what it does, if you're having categorical and categorical, it can do a chi-square test, just to see whether there is independence between the two variables, so like here and here. And then you can see like gender and also compared to diabetes. Then it will give a p-value automatically, and it will tell you at the bottom there which test it has done. But however, you can also specify the type of test. So quickly, we also did some visuals. So using ggplot, you can see we have here a box count plot, and here this count plot, or the bar plot, you can see it's for gender, the distribution. So what we decided next is to drop the column other, because there are very few individuals and therefore may not offer conclusive estimates at the end. So that's what we do. We go ahead and drop them. Using this, we filter not equal to other. For the enrollment by race, we see they are almost equal around, given the races that were documented in the data set. You can also do a box plot of the blood glucose sugar by maybe smoking history, or blood sugar also by diabetes, and we see individuals who are diabetic have a slightly elevated blood glucose levels. You can also do a visualization to see enrollment by state, because in our data set we had this column locations, which were the United States states where the participants were enrolled from. So from the location, what we noticed is that some individuals documented districts rather than the larger state, and others mentioned the country. So for what we did here, in order for uniformity, we just went ahead and like the District of Columbia, which is in Maryland, we just write Maryland. Then Guam, we converted to Hawaii. And then for the ones who mentioned United States, we just assume that it's Washington. So that's what we did here. That's the first step that we're doing here. So we are just converting that. Then to do this, we are using the plotly function. And what the plotly function does, plotly uses the US states coordinates to visualize. So to do that, I went ahead to this website and scraped this column so that we have a state and its abbreviation. then came back to R using web scraping. If you haven't watched my video on web scraping, you can take an opportunity and see it, and just to get to understand how we do the web scraping. Then lastly, we join the data so that we can have enrollment by state as shown here, so that we have year, state, patients enrolled, so the number of patients enrolled, and of course the abbreviations of the state. Then finally we mapped, we use the plotly function, and to do this I am adding a video to a YouTube channel that I also enjoy on R programming, so that you can be able to understand what happens here. But just in a nutshell, we are able to generate an interactive plotly visualization where you can go ahead and just see how many individuals, and also it can be able to progress towards the years. So I think that's all for the visuals. So we move on to the step of building the logistic model. And the first thing we're going to do is drop the columns that we don't need, which is the year column, the location, and for BMI, because we've created the BMI category, there's no need of going ahead with this. We'll just be adding collinearity to our model, and it will be a little bit disadvantageous. Next, for the race columns, the other cleaning that we're doing. So for these race columns, we see that they were separated so that it was a binary response for each race: African American, race Asian, race Caucasian, race Hispanic, and other. Everything was binary response. So what we do, we just want to go ahead and have one variable that collapses all of this. So to do that, we're using if else and our output, and then lastly we just drop those columns. So if we go ahead and just see our data set again, this is what we have. We have the last column here. Then for the variables that are factors, so we just convert them into factors, and the reason for this is because we want to change the reference to have a desired reference group. So this is what we do. So sometimes you want, when we'll be interpreting our model, we'll be comparing, let's say, male to female. So, or we'll be comparing overweight to normal weight based on the BMI category. So when you want to change your reference group in R, the first thing, you ensure that your data is in factor. The second thing, now you come and take that column of interest. So like here, we're extracting diabetes and the gender column. Then we are editing it. So we are editing it, and then we are saying using the relevel function. So the relevel function takes the data set, and then it takes the gender. The data set, takes the column. So the relevel function takes the column, and then you go ahead and just say the reference group that you're interested in. So that's what we do here. So we change the one for hypertension to be no, we change for the heart disease to be no also, and for the smoking to be never. Next, we split the data into train and test set. So for doing this, the first thing, we set seed so that our data can be reproducible. So set seed 1, 2, 3 for reproducibility. And then we just sample our data, and then we sort and take 70% of it based on the number of rows. Then the first 70% in the split ratio, we extract that to be our train, and the remainder is our test set. There are many other ways of splitting data. This is just one of the ways on how to split into train and test set. If you wish to do maybe 80%, ensure you change here to 0.8. And then now we just build the model. So to build the model, we are going to use the GLM function in R. So we are creating our model to be called diabetes underscore model. This is our model element. Then it takes the function GLM, your Y variable, then use the tilde sign. So the tilde sign, then this tilde versus, it's like just saying versus. If you wish to have several columns in your data set, so I'll go and use the train here. So if you wish maybe not to include maybe BMI class, so you'll just go ahead and say gender plus age plus hypertension plus heart disease and so forth, just as we discussed the first video in linear regression. Then the next thing, after taking in that, so we've mentioned the Y variable versus the X, then state your data. So our data is dataset underscore train. Then lastly, we do the family equals to binomial. So you can do family equals to binomial in quotes, or alternatively, you can go ahead and see the help of GLM. There are also two other ways in which you can do so. Apart from just saying family equals to binomial, you can go ahead and choose the logit function. So you can go ahead and just say alternatively, you can say family equals to binomial, and then in bracket, link equals to logit, and it will still do the same. It will still do the same way. So our output, you use the summary call to give you this output, and we can just go ahead and explain it. So for this, what we have here, we have it's saying now gender equals, so we have the coefficients here, then we have the estimates and the standard error. So in our introductory video, we said when we are modeling our logistic regression, the GLM allows us to model the mean of the response. So because it's coming from a Bernoulli distribution, so the mean is the probability P. So the mean, so the log of P over 1 minus P is given now, gives us these estimates now. So like here for the beta naught now, how do we interpret this? So beta naught is when everything else is 0, all our x's are 0. The expected mean now of the distribution is now this. So this is the log odds. So negative 2.563 times 10 raised to power 1. So this is what we have. And something else we have here, we also have the significance of each estimate. So I'm going ahead and explain some of them. So gender male compared to gender female. So what it tells us here, males have the log odds of male experiencing diabetes are 2.59 times 10 raised to power negative 1 compared to female, assuming all other factors are constant. That's how we interpret. And then the same for age. Given a unit increase in age, the log odds of experiencing diabetes are 4.55 times 10 raised to power negative 1. So we also mentioned how we do, instead of interpreting the log odds, we can use the odds ratio. So what is required for the odds ratio? We just require to exponentiate these estimates, and we'll see that in the last table. So quickly, we can go ahead and also just to see how our model performs. So in the classification metrics, performance metrics for classification, we mentioned that we can use the confusion matrix to generate metrics such as accuracy, F1 score, and so forth. So this is what we have here. What we do, we import the library caret, which allow us to use the confusion matrix. Then we generate the predictions now. So for the predictions, we use the predict function in R. What it takes the formula, which is the model that we stored, then the new data set. So remember, when you are evaluating a model, you don't want your model to use the same data set that it was trained on. So you give it new data set that it hasn't seen, so which is the test, and then the type of response. So because we are doing logistic regression, we want to model probabilities, and that's why we say response. So when we do that, we get to see, we have, and call out pred1. We see there are just some probabilities here in my console here, so it's just a list of probabilities. Then for the predicted data, like how we mentioned in the sigmoid function, those are 0.5 and above are said to be 1. Then below 0.5 are converted to 0 because our binary response. So this is what we are doing here. We are saying go ahead and see pred1, these probabilities, those ones which are greater than 0.5 or equal to it, return them as yes, else return them as no. Remember, the reason we did this yes no is because R can be able to model even with text data, the factors now, the yes and no, rather than 1 0 for logistic and the linear regression. Then what we do is just compare the predicted data versus the actual data. So how does it perform? So we get this confusion matrix. So remember our confusion matrix, how it looks. We have the true positive, which are those ones which are positive and have been predicted to be positive, and we see our model has 1625 of those. And then no, so this is the prediction and this is the reference. We have 27, 139. We see that there are those which were positive but have been predicted to be negative. So what are those ones? We have 982, and then we have also those ones which were negative but they have been predicted to be positive. So these are false positive, 249. When we go ahead and see our accuracy, which will be now this plus this divided by everything else, we have our model performing 95.9% accuracy. We have sensitivity and specificity. So we have which sensitivity of 99.09, but we have a very low specificity. Remember, our classes were imbalanced, and when we were mentioning about recall, and if your model is a little bit biased, recall won't be a good metric. And we see here because our negative classes are very high, and that's our challenge. So I've added a description here, trying to talk about that. It performs well in detecting diabetes, but it could improve well in specificity. You can also print the F1 score, and you can install this package ML matrix from Cran, and then what it will do, you just call it out, then use the function F1 score and the Y variable versus the predicted data, and just say positive equals to null. So it gives you a F1 score of 97.78%, which is pretty high. Lastly, one of other metrics, or the second last, we can also use the likelihood ratio test, and this is just like using a Pearson chi-square test. We are comparing this model to a null model. So a null model means a model without these predictors, age, gender, and so forth. How well does your model do without another model? So we see we have a p-value of 0. So p-value is less than 0.5 indicates that the more complex models provide a significantly better fit. So the model with now our parameters, and this is what we have. You can go ahead and use the ROC curve. I've added this function on how to compute the true positive rate and the false positive rate. And what it does here, we just be able to see that our model has this our sensitivity versus specificity curve, and we have a accuracy of area under the curve of 80.7. Not so good, but it can work well. So as a bonus, we were tabulating the estimates of our logistic model using publication-friendly formats. The first way is using the SJ-plot, and the SJ-plot, we just run these functions here, and what it does, it will output this package here, which I've gone ahead and zoom it out, and it opens in the browser, my default browser. So this is what we have here. We have the predictors, the coefficients, and so forth, just as what we had. But now the difference now here is, instead of the log odds, they've been exponentiated to be the odds ratio. Then you are given a confidence interval, which is 95%, and a probability whether they are significant or not. So for example, a blood sugar level, given unit increase in blood sugar level, the odds of experiencing diabetes increases by 1.03. That's the odds of getting the risk increases by 1.03, which is 3%. Alternatively, you can use the GT summary function as we did with the linear regression, but now our method is GLM rather than LM. And then since we are using GLM, we choose the family of the GLM to be binomial. And then it's just the same as what we did in the linear regression. You can check the video of how we did it there. So the other thing that we are adding different is the exponentiate. In the linear regression, we were saying equals to false, so that here we are telling, please go ahead and exponentiate the coefficient, so that rather than having the log odds, we'll be having the odds ratio. When we do that, we have this table. Which is really good. So we have what we have here. What we have here is one of them. We have the univariate versus the multivariate, the adjusted versus the unadjusted. So we go ahead and say for males, male individuals have 1.31 odds of experiencing diabetes compared to female, assuming all other factors are constant and this coefficient is significant. When adjusting for all other factors, the odds of male experiencing diabetes are 1.30 compared to female, and the estimate is still, and this odds ratio is still significant. What about smoking history? Current smokers are at 1.58 more times risk of experiencing diabetes compared to those who have never smoked, assuming all other factors are constant. When adjusting for other factors, current smokers are 1.41 times of experiencing diabetes compared to those who have never smoked, and the estimate is still significant. So remember what we talked about in the first video when we were talking about linear regression is that when you're having a univariate model, you are asking that X variable to explain all the variability in the Y variable, and it may end up overestimating, similar to what we have here. So we see that the odds when heart disease alone, assuming other factors, is 5.85, but when we adjust, the odds becomes 2.03 because now we are building a model that has adjusted for all other factors. So there we have it. This is what we've been able to do. So what can you recommend based on this? I've gone ahead and also just added a description of this here. So the model interpretation in detail, age was positively associated with diabetes. Each additional year was associated with 5% increase in the odds of diabetes. And I've added also some key takeaways so that we see that heart disease doubled in odds, race was not significant, and gender, but glycemic indicators and also BMI were very strong predictors. So in summary, our regression model has been able to model a couple of indicators to diabetes, and we saw that glycemic indicators were very significant. You can recommend, for policy recommendations now as a data scientist, you can recommend strengthen community-based screening programs where you can leverage on BMI, age, hypertension history for risk-based screening, especially in settings where laboratory settings for this is inaccessible. So in the communities where maybe rather than waiting for a blood screening, you can use these factors to already predict diabetes to allow for timely detection and referral. You can also do targeted obesity campaigns, so that you can educate the community to avoid against diabetes because it puts them at a very high risk. And then you can also integrate cardiovascular risk management because we saw a very strong association between hypertension and heart disease. Therefore, individuals who are already diagnosed with hypertension and heart disease, more clinical assessments needs to be done or integration so that they can be assessed for diabetes also earlier on. Finally, you can do tobacco cessation interventions, and you can also utilize HbA1c. You can see how it can be used for clinical settings. So there you have it, guys. This has been one of the longest video yet. So we've been able to fit the logistic regression model in R. In later videos, we'll go slow a little bit on the EDA so that you can go directly to the model. But like other videos, I've also added timestamps so that you can be able to skip to sections that you are interested in. I'll see you in the next one, and if you've enjoyed this video, ensure you subscribe and share it with your friends. Bye for now.